Now let us talk about Kepler's laws of planetary motion. You should understand that this is a kind of historical approach to this chapter of gravitation. The time when Newton was present, around you can say 1680 AD, but Kepler was before him. Newton has given the formal description of everything, or rather you can say he was the first man to develop science. If you try to discover a little bit of the history of the time when Newton was present, that was the time when church was very dominant and a free scientific research was not permitted. If you talk about the celebrities which came before Newton, just before him was Johannes Kepler, before him was his teacher Tycho Brahe, before him was Galileo, and before that you can say Nicholas Copernicus, and much before that was Ptolemy. This is the way things have progressed. But Newton was the first man to present everything in a scientific manner, and because of which the dominance of church vanished. Newton ने जितनी सारी laws दिए, सारे mathematical expressions, using that हमने ये gravitation के chapter को discuss किया है. But right now we are trying to discover a historical aspect that whatever Newton said, before him Kepler also said the same thing, but without using any mathematics, just on the basis of certain observations. As I said that the time when Newton was there or before that, it was not allowed to make scientific research, and because of which there was a person called Tycho Brahe. He went to an island and started making observations of stars, because that time the controversy which was going on, that which is at the center and who is rotating about it. Some people used to say that everything rotates around the earth, some people used to say everything rotates around the sun. Then Tycho Brahe was the person who got into this idea that in case we make the maps of the night sky every week, then after analyzing that map something can be drawn. And it was almost for 25 years, every week he made the picture of night sky, which he could not analyze, rather his student Johannes Kepler analyzed and came up with 3 laws. Let us first discuss the laws, then we will see how they could be derived from Newton's law also, and how we can appreciate how big a brain Johannes Kepler had. The Kepler's laws essentially have 3 aspects. The first law is called the law of orbit. This is called the law of orbit. Before we discuss this law, there is a prerequisite to know about ellipse. Let us get ourselves introduced to the concept of ellipse. If you, let us suppose you have a drawing board, you put 2 nails and tie a thread which is having a larger length compared to these 2 distance, the distance between these 2 points. Then you put your pencil so that the thread is stretched, and then you start moving your pencil. You understand the concept? On a drawing board आपने ये 2 nails लगाए हैं जिसमें एक thread को lose करके आप यहाँ पे tie करेंगे. Then you pull your pencil so that ये thread आपका straight हो जाए, tighten हो जाए, and then you move the pencil. If you move the pencil, you will be coming across this kind of shape, and this is called an ellipse. अंडरस्टैंड? इसमें आप देख सकते हैं कि इसका एक साइड जो है वो ज्यादा लार्जर लेंथ का होगा और दूसरा साइड जो है वो स्मॉलर लेंथ का होगा. दिस इज एसेंशियली द फीचर ऑफ एन एलिप्स. इसके दो पॉइंट जो हमने लगाए थे दे आर कॉल्ड फोकस. इसका वन साइड विच इज ऑफ लार्जर लेंथ, उसकी आधी लेंथ को जनरली हम ए से इंडिकेट करते हैं और जो दूसरी साइड की लेंथ है दैट इज डिनोटेड बाय बी. So here you can see this A is called semi major axis and this B is called semi minor axis. Also the distance between the center and the focus, everything is symmetrical. जितना distance इसका यहाँ से है same distance this focus has got from the center. This much distance is indicated by A into E, where E is called eccentricity of the orbit. एंड एलिप्स के लिए ई की वैल्यू 1 से कम होती है. दीज आर सम ऑफ द फीचर्स यू हैव फॉर एन एलिप्स. इन सब चीजों की जरूरत पड़ती है जब भी आप केपलर्स लॉज को समझने का ट्राई करते हैं. सो हियर यू शुड अंडरस्टैंड इन दिस एलिप्टिकल ऑर्बिट वन साइड इज ऑफ लार्जर लेंथ, अनदर साइड इज ऑफ स्मॉलर लेंथ. लार्जर आधी लेंथ जो है दैट इज कॉल्ड सेमी मेजर एक्सिस, पॉपुलरली डिनोटेड बाय स्मॉल ए, एंड दूसरी साइड जिसको हमने स्मॉल बी से इंडिकेट किया है दैट इज कॉल्ड सेमी माइनर एक्सिस. इसके दो फोकस हैं और सेंटर से एक फोकस का जो डिस्टेंस होता है आइदर दिस डिस्टेंस और दिस डिस्टेंस दैट इज ए टाइम्स ई, वेयर ई इज कॉल्ड एक्सेंट्रिसिटी एंड दिस इज लेस देन 1. यू अंडरस्टैंड? नाउ वंस यू हैव अंडरस्टूड दिस कॉन्सेप्ट ऑफ एलिप्स, देन यू आर इन ए पोजिशन टू अंडरस्टैंड दिस लॉ ऑफ ऑर्बिट. As I said, all these laws of Kepler, they were based on observations of the charts, the diagrams, the pictures, which his master Tycho Brahe had made. And night sky में उस समय में जितने भी planets थे, and mind you by that time Galileo had already invented telescopes and those equipment were available to make the observations. तो उन्होंने सारे जो planets थे available उनकी ऑब्जर्वेशंस बनाई थी. माइंड यू दैट टाइम यूरेनस, नेपच्यून, दीज वर नॉट विजिबल, दे वर ऑलरेडी सिटिंग ऑन द अर्थ. सो यू कैन से लेफ्ट ओवर 5 प्लैनेट्स वेयर देयर जिसका उन्होंने डायग्राम बनाया होगा. एंड दिस लॉ विच ही अराइव्ड एट सेड दैट all the planets, maybe 5 planets, revolve around the earth in elliptical orbit having sun at one of the foci. This was his statement. That meant that maybe this is the elliptical orbit of, say, Mercury. This is Mercury. Then it must have had 2 focus, one focus and another focus. Then on one focus sun was present. On one focus sun was present, another focus must have been vacant, and Mercury was rotating in elliptical orbit. Now in case Venus was there, it must have been on some other elliptical orbit, maybe of larger size. Again you see in this elliptical orbit, if Venus is rotating, then it has 2 foci, one is this, another one is this. Second one is vacant, on one focus sun is present, and like all the 5 planets he might have observed, this is the way he concluded. It was a very great thing to observe because you see he was already sitting on the earth which itself was moving, and he had to make the observation imagining that he is still. It is said that probably he must have used Mars as the lantern, and then he might have concluded how these planets around the sun, they are revolving in elliptical orbit. You see, this is a very great observation. Just imagine that he had 25 multiplied by approximately 50 diagrams, because every week the diagram was made, and just by looking at these diagrams he had concluded this. So long as reading of this law is concerned, it is a very simple statement that all planets revolve around the sun. But just try to think how he could arrive at this particular conclusion. He was already sitting on Earth, which is rotating in elliptical orbit, and from there, just by imagining the position of all other planets over the years, he concluded on this particular fact without any mathematical explanation. Of course, later on Newton gave the mathematical explanation to these elliptical orbits by saying that energy was lesser than some particular speed or energy was negative. As you have already seen in the trajectory part, we have proved that the path can be circular or path can be elliptical depending on what kind of energy it is having. If it is moving with an orbital speed, then the path happens to be circular. But in case the energy is slightly more or slightly less than that, then the path becomes elliptical. But that was the thing said by Newton with the help of a lot of mathematics. But try to understand that Kepler was before Newton, and he gave this particular theory just by his observation. So this was the law called law of orbit, in which we essentially said that all planets revolve around the sun in elliptical orbits, having sun at one of the foci. Now let us look at the second law, that is called law of area. Now let us look at the second law, that is called the law of area. Consider any planet, say the Earth, the orbit is elliptical, and at one foci sun is present. This is the sun about which this Earth is rotating in elliptical path. Now Kepler said that if you say consider the situation of the Earth right now and make a position vector from the sun to the Earth, and consider the position of the Earth say after a week, then the position of the Earth must have been here. Again you make the position vector here. It will have certain area involved. You understand? This area is essentially between two position vectors, maybe over an interval of a week. Now imagine the position of the Earth after 6 months. It might have been here. This is the new position of the Earth, and from there again a time interval of a week, maybe the position must have been here. Again you draw the position vector for two positions spread over an interval of a week, and again you find out the area of this portion. Then Kepler concluded that these two areas are same. You understand? He said that the position vector of any planet from the sun sweeps out equal area in equal interval of time. This is a very great conclusion he could draw. First of all, he ascertained that the orbit is elliptical. Now in a particular elliptical orbit, he observed that the position vector of any planet from the sun sweeps out equal area in equal interval of time. Maybe he might have taken interval of time to be a week or maybe a month. ये अर्थ की पोजीशन यहां से यहां अगर एक वीक के बाद दिखाई गई है, तो यहां पे भी अर्थ की पोजीशन एक वीक के बाद दिखाई गई है. And whatever semi triangle kind of form you are seeing, he observed that this area and this area, they are same. This is a very great observation. And try to think how the first thought might have come in his mind that the sweeping out area in equal time interval is equal. It's a very great conclusion. However, this is other thing that Newton later on proved this particular law with the help of his mathematics. Newton could give the explanation, Newton's explanation to this particular law of Kepler was that he said that aerial velocity means the velocity with which, or you can say the rate with which area is being covered, this is equal to simply the angular momentum upon twice of mass of the satellite. You understand? जो लॉ केपलर ने अपने सिर्फ ऑब्जर्वेशंस पे दिए थे, उसको एक्सप्लेन करने के लिए न्यूटन ने मैथमेटिक्स यूज करके ये प्रूव कर दिया दैट द एरियल वेलोसिटी, दैट मींस एरिया अपॉन टाइम कैन बी रिटन एज द एंगुलर मोमेंटम ऑफ द सैटेलाइट अपॉन ट्वाइस ऑफ मास ऑफ द सैटेलाइट. दिस इज द फॉर्मूला ही अराइव्ड एट. एंड देन न्यूटन सेड दैट if you have any planet, then torque acting on it is zero because the force involved is central. You understand? In case you are looking at the position vector of the planet, it is somewhere here in this direction, and force is acting in opposite direction. In case force and position vector they are in opposite direction, then torque will become zero, because we have already seen from the definition of torque is that it is equal to R cross F. And in case the angle between R and F is 180 degree, then it is RF sine 180, that is equal to 0. So Newton said that whenever a planet is under the motion of a central force means the gravitational force by the central object sun, then torque acting on it is 0, and as per the principle of conservation of angular momentum, when torque is 0, angular momentum becomes constant, and once angular momentum has become constant, then the aerial velocity, that will also be constant. This is the way Newton proved it. But this is an amazing fact that Kepler arrived at this particular law just by way of observation. So long as practical aspects are concerned, we may ask you certain numerical questions based on this, or maybe we may ask you to recognize this expression that aerial velocity means area divided by time is equal to angular momentum upon twice of mass. This is the expression on the basis of which we may ask you some numerical questions. Now, these were the two laws Kepler gave within a span of few years, but after a gap of several years, he arrived at the third law, that is called law of periods. So let us look at that. Now let us look at the third law, that is called the law of periods. Imagine the elliptical orbit of any planet, say the Earth. You have already seen that this much distance is called the semi-major axis. Sun is present here, or maybe Earth is rotating. Then Kepler concluded that the square of the time period of any planet around the Sun is proportional to cube of the semi-major axis. This was the conclusion he made just by way of observations. This is really very astonishing fact that without any mathematical explanation, just by observation, he gave this third law, which of course Newton proved with the help of his mathematics. If you have done that orbital speed of a satellite, we have just now derived that the net force towards the center, that was equal to m omega square r, and that omega was replaced by 2 pi by t. So here also you can see, if you do the cross multiplication, there also he had proved it. But mind you, this was the mathematical explanation given by Newton. But before Newton, Kepler, without using any mathematics, just by way of observations, he concluded at this. and try to appreciate his thinking, that how could he think that the distance can be related to the time period of a planet rotating around the sun. It's a very amazing fact. And sometimes it is said that all of us together along with our supercomputers, probably we are not as conclusive as Kepler was at his time, because looking at these charts and without much of mathematical help or anything else, he could arrive at all those results which great Newton could do only after a lot of mathematics, only after a lot of calculus and all. So that was the beauty of Kepler's laws of planetary motion. It was just for the historical interest that we happen to study, so that you can appreciate whatever we are doing with the help of mathematics that was earlier given just by way of observations. So long as practical aspects are concerned, we ask some numerical question based on this particular formula, that time period is proportional to a raised to the power 3 by 2. We may ask you a numerical question based on this expression. Say they can give you that the orbital radius is something and time period is something. Then in case the orbital speed is different, how will be the time period dependent on that? So if you modify this expression, then you can say T1 square by T2 square. This is equal to A1Q upon A2Q. This is the way you can use this expression. Now let us have an example based on all the Kepler's laws of planetary motion we have understood, and how the eccentricity of the orbit was involved and so on. Let us have an demonstrating example based on that. Let us have an example on Kepler's law. It is given that a particular satellite is rotating in an elliptical orbit, and you know that the eccentricity of the orbit is related to the distance between a focus and the center of the ellipse. You have been given E. Given eccentricity of the orbit has been given, and you have to find out the ratio of maximum speed to minimum speed of a satellite rotating around it. Maybe this is a case of sun and some planet is revolving around it. Then you see this point which is very close to the sun, rather you can say closest to the sun, this is called perigee. This point P is called perigee. And the point which is farthest from the sun, this is called apogee. Or this is also called perihelion and aphelion. These can be the names. Now you see, when the planet is approaching the sun, when it is at a closer distance, then its speed becomes very large, and it is going farther off, its speed becomes less. You have already seen that farther you are from the central object, your speed is less. So you must understand that when the planet has reached perihelion, its velocity will be maximum, and when it is aphelion or farthest distance, its speed will be minimum. You understand? Its speed will be minimum at this point and its speed will be maximum at this point. And so long as distance are concerned, you have already seen that this much length is A into E. This much length is A. Now, if I see this situation of perigee, the distance of this point from the sun or center, focus, whatever you call, I am denoting by R minimum, and the distance of this apogee from the sun I am denoting by R max. You understand? Now if you look at the geometry, you can say that R max is A plus AE. R max can be written to be A plus AE. But if you talk about this minimum distance R minimum, this R minimum is total A minus AE. You see that this R minimum is the length of semi-major axis minus A into E. So R minimum can be represented as A minus AE. Is it clear? The maximum distance and minimum distance, they have been represented in terms of semi-major axis and eccentricity. Eccentricity is given to you. Now you have already seen that the indirect conclusion of constant aerial velocity is that angular momentum is also constant. If we say that aerial velocity is equal to constant, that was the second Kepler's law, and Newton said that aerial velocity is angular momentum upon twice of mass. This is also equal to constant. Therefore, you can say angular momentum is equal to constant. This is very much obvious. अगर aerial velocity constant है and aerial velocity angular momentum upon twice of mass है, mass तो constant है ही, so angular momentum भी constant होगा for a satellite or planet revolving around the sun. Now जो दो position की हमने यहाँ पे बात की है, for example perigee and apogee, you can clearly see यहाँ पे R और V के बीच में angle 90 degree है. When you had talked about angular momentum, then you had said it was R mv sin theta. तो यहाँ पे theta जो है वो 90 degree है, whether it is a case of apogee or it's a case of perigee, the angle theta is 90 degree. So angular momentum can successfully be written as mvr, R into mv into sin 90. So at these two places you can say that mvr is equal to constant. And from this expression as well you can understand that जहां पे R की वैल्यू ज्यादा हो गई होगी वहां पे V की वैल्यू कम हो गई होगी. In case you want the product of V into R constant, because mass itself is a constant, तो जहां पे भी R की वैल्यू ज्यादा है वहां पे V की वैल्यू ऑलरेडी कम होगी, and that you have already shown. यहाँ पे R की वैल्यू आपने मिनिमम शो की है, तो यहाँ पे आपने वेलोसिटी की वैल्यू मैक्सिमम दिखाई है. You can clearly see from this place. जैसे जैसे डिस्टेंस ज्यादा हो जाता है वेलोसिटी कम हो जाती है. सो आई मस्ट से दैट एट पेरिजी एंड अपोजी दोनों जगहों पे आप mvr इज इक्वल टू कॉन्स्टेंट लिखेंगे. दैट मीन्स v इंटू आर इज इक्वल टू कॉन्स्टेंट, बिकॉज मास तो कॉन्स्टेंट है ही. सो जहां पे मैक्सिमम स्पीड है वहां पे r मिनिमम है, और जहां पे स्पीड मिनिमम है वहां पे R मैक्सिमम है. अंडरस्टैंड? फ्रॉम दिस एक्सप्रेशन इटसेल्फ वी हैव कम अप टू दिस कंक्लूजन. ये पेरिजी की सिचुएशन हो गई और ये एपोजी की सिचुएशन हो गई. नाउ इन केस यू हैव टू टेक द रेशियो ऑफ दीज टू, V मैक्स अपॉन V मिनिमम अगर आपने कैलकुलेट करना है तो दिस इज एसेंशियली R मैक्स upon R minimum. You can write this thing is clear. And R max की जगह पे आपने लिखा है A plus AE और R minimum के जगह पे आपने लिखा है A minus AE. So you can write it here as A plus AE upon A minus AE. Here you can cancel out A, and finally you will have this result that V max upon V minimum is 1 plus E upon 1 minus E. You can directly use it as a result also. अगर हमें कभी किसी ऑर्बिट की एक्सेंट्रिसिटी दी गई है, एक्सेंट्रिसिटी बेसिकली ये डिसाइड करता है कि इस ऑर्बिट का जो शेप है वो कितना कॉन्ट्रैक्टेड है, कितना डायलेटेड है. ई की वैल्यू एक एलिप्स के लिए 1 से लेस दी जाती है. इन केस द वैल्यू ऑफ एक्सेंट्रिसिटी हैज बीन गिवन, then you can find out what is the ratio of maximum speed to minimum speed of a planet revolving around the sun, or maybe any artificial satellite revolving in elliptical orbit about a central object. जो एपोजी होती है वहां पे स्पीड इसकी मिनिमम होती है, और जो पेरिजी होती है वहां पे इसकी स्पीड मैक्सिमम होती है. सो दैट इज ऑल our today's lecture. So before we move ahead, let us try to recapitulate what we all discussed in our today's lecture. In today's lecture, continuing in the chapter of gravitation, we first covered the satellite motion. In the discussion of satellite motion, we talked about the orbital speed, how it was related to escape speed. We talked about the trajectory. We talked about the time period. We talked about the energy. Then we discussed a concept of weightlessness. Inside a satellite, why weightlessness is present, what are the biological aspects of weightlessness. Then we talked about various satellites, like practical aspects of geostationary satellites and polar satellites. How the altitude is related to time period and so on. What is the orientation of these practical satellites we launch. Then we had a discussion on some historical aspects of the chapter of gravitation. That was with the help of Kepler's laws of planetary motion. We gave the three laws which Kepler had given before Newton, just by way of observing certain charts. And of course we side by side gave the Newton's explanation to, rather Newton's mathematical explanation to all the Kepler's laws, which were made just on observations. So now that essentially brings you to the end of the chapter of gravitation. In the next chapter, we will talk about the mechanical properties of solids. Thank you.